Good morning, everyone. My name is Andrea Layedra. I am PhD student, and my doctoral research focuses on studies in C. elegans through the applications of microfluidic devices. The study that I'm presenting today is called a microfluidic device for simple quantifications of chemotaxis with C. elegans in neurotoxicological studies. As a background, nowadays, toxicology must meet two opposing demands. First, the analysis of a growing list of chemicals, including pesticides, that are developed to many important purposes, like protection against crop loss and against vector-borne diseases. However, there are significant concerns over the potential toxic effects of pesticides to non-target organisms, including humans, which may even cause neurodegenerative diseases such as Parkinson. And the other demand is the resource limitations and ethical concern associated with traditional mammalian testing. In this sense, C. elegans is a useful model that has been applied in many research to study human neurodegenerative disorder. C. elegans is able to detect external chemical signals and perform chemotaxis behavior through its simple chemosensory system. So here we propose that the neurotoxic effect of xenobiotics could be reflected in the chemotaxis behavior of this nematode. Here you can see the traditional method to perform chemotaxis assay. C. elegans chemotaxis is traditionally assessed on agar plate. To briefly describe this method, a point source of a particular chemical is placed on an agar plate for establishing a concentration gradient of this compound. Worms are then placed on this agar plate and left to grow. The chemotaxis behavior is analyzed by counting the number of nematodes in the source area of the chemical. However, this method suffers from several disadvantages for obtaining reliable data. First, the conventional methods are rather time-consuming due to the slow diffusion of chemicals in the agar plate. Second, the ability to create and maintain a desired shape of the chemoeffector gradient is critical for the analyzing chemotaxis of C. elegans. However, it is difficult to control this gradient with this method. And finally, only the number of nematodes in the area containing the highest concentrations of chemoeffector is counted for the analysis. Chemotaxis to other lower concentrations of chemoeffector is difficult to be examined on one plate. It's for those reasons that new technologies such as lab-on-a-chip devices have been developed. These lab-on-a-chip devices are used as analytical assistants for handling of organisms. Between the main advantages are low cost of manufacturing, is handling of nematodes, and in this case, the nematodes are loaded by suspension. Regarding the materials, this device can be made of different materials. However, I'm focusing in PDMS. Unlike other materials, PDMS is used for biomedical applications, cell cultures, implants, among others, due to its properties. PDMS is a silicone elastomer. It's biocompatible, have high oxygen permeability, is transparent and economical. So, with the aforementioned, we propose the following objectives. First, develop microfluidic device for toxicological studies. Second, determine a methodology for chemotaxis analysis using microfluidic device. And finally, the applications of this device for toxicological assays. Regarding the first objective, we designed and made this microfluidic device with the following methodology. Design is elaborated using a Corel program with desired dimensions. This design is printed on a polymer that serves as a base for a epoxy resin mold. Then this mold is filled with PDMS where more replicates can be generated. The PDMS device is bound to a glass slide using a plasma. Here you can see the designs we are working with. This is the one I will talk about today. And to make a parenthesis, we are using this one to measure offspring in reproduction assays. This works as a filter to collect the offspring while the adult nematodes remain in the device. In addition, each device has 3 repetitions. Okay, following with chemotaxis, the second objective was to determine a methodology for chemotaxis analysis. The design consists of an intermediate curved channel in which the nematodes are placed. Besides, it has 2 separate straight side channels, one of them for the tractant and the other one for the diluent of the tractant. Diluent and the other one of the tractant. Okay, therefore, the device is divided into 2 zones. Diluent area and the tractant area. Now, which is the procedure? First, the nematodes, in this case N2 strain, are placed inside the microfluidic device and they are distributed along the curved channel. Then the tractant is placed in one side, while the diluent of the tractant is placed on the opposite side. Finally, the nematodes are counted on each area of the device at different times. Here you can see a video. This video is just to show you the results of the device load with nematodes and test compounds. At this point, we established 2 questions. The first one, which compounds cause the stronger attraction inside the microfluidic device? To answer this question, we test some of the following attractors, confronted with the diluent. The attractors were E. coli, hexamyl alcohol, sodium chloride, and 2-butanol. These results show that the greatest attraction for the nematodes was to 2-butanol, followed by hexamyl alcohol and E. coli. These data represent the control of 2-butanol. It means to confront the butanol diluent, which is ethanol. For that reason, we select the system ethanol to butanol. At the same time, the second question was, at what point is the highest chemotaxis index obtained? For this, the nematodes were counted at different points in the time for 3 hours. In the left side, you can see photos of the movement of these nematodes at different times. The red arrows show how they move to the attracting area. We counted the number of nematodes and then we calculate the chemotaxis index using the following expression. Number of nematodes in the attracting area minus the number of nematodes in the diluent area divided to the total number of nematodes. As you can see in this image, the highest chemotaxis index occurs at 115 minutes and then begins to decrease slightly. It's for this reason that this time we selected as the minimum time for the following test. In summary, up to this moment, we have the system 2-button on, at this time. With these parameters determined in the device, we proceeded with the third objective, which is the application of the device in toxicological tests. For this, first we treat the nematodes with these 4 compounds: paraquat, glyphosate, cypermethrin, and cialotrin. And after, we evaluate their chemotaxis behavior with the system aforementioned. Here you can see how we calculate the chemotaxis index 2-button on and the results of chemotaxis to each treatment 150 minutes after. And these were the results obtained. As you can see, in relation to the control, the treat nematodes have a lower chemotaxis index, being more evident in the treat nematodes with glyphosate and cialotrin, which also have a greater dispersion. In conclusion, microfluidic device can be designed for different applications. One of them is to apply them to the behavior of nematodes as chemotaxis assays. The methodology for the applications of the microfluidic device was determined by the selection of the extractant that was 2-button on and the time to 150 minutes at which the chemotaxis index was highest. The microfluidic device could be applied to toxicological assays to determine the chemotaxis of C. elegans after being treated with different compounds. Well, that is all. Thank you very much for your attention, and thank you also to my team working on C. elegans and microfluidics.